脑人言。
感觉 neuroscience 是他空下来随便做着玩的，但就是说随便一做呢，就解决了我们这个大脑怎么把外部信息变成我们做决策的依据的这个问题啊。所以我们今天就特意请他来亲自讲一讲他们最近发表在自然通讯上的这篇工作。那么好像张博士会用英文做报告是吧？
对对，我看。
那我们提问、讨论中英文都可以啊。期间姚涛博士也会留意大家的留言提问，那么在恰当的时机来请张博士给大家解答。那所以那张博士我们就开始。
好，多谢这个脑人言邀请我今天过来给大家讲一下我博士期间的工作，然后也多谢薛博士的这种抄底儿的介绍，谢谢。那这个工作是在中学院杨老师的指导下完成的。然后对，像那个薛博士刚才说的，我会用英文讲，然后大家提问的话就随时打断，然后中英文都可以。Okay, let's get started. Decision making has been started for decades, and most tasks used for starting decision making are so-called two-on-turn-tails forced choice tasks, which means subjects need to make a decision between two on-turn-tails based on presented cue. And to explain the behaviors in those two on-turn-tails forced choice tasks, psychologists proposed the drift diffusion model, DDM for short. And in this model, it assumes there is an integrator who accumulates the evidence supporting one option, H1, and against the other option, H2. And at each time step, the agent will observe or sample a piece of evidence, and the accumulated evidence will get larger when the observed evidence supports the choice H1, and it will get smaller when the evidence supports option H2. And the agent would stop sampling and make a final decision when the accumulated evidence hit one of two predefined boundary. And here, when H1 is chosen if the positive boundary is hit, and H2 is chosen when the negative boundary is hit. And quite amazing, researchers found this accumulated evidence signal in the lateral interparietal cortex, LIP. And LIP, I think, is the first brain area that was found to encode the accumulated evidence in the decision-making tasks. And it receives sensory signals from the MT and MST, and project to the oculomotor control area like the frontal eye field, FEF, and superior colliculus, the SC. And based on this anatomical structure, it's quite reasonable to guess that LIP is very important for the sensory to action transformation. And in fact, it's indeed correct. And like many other visual cortex, LIP neurons are active when a salient visual stimulus is shown in the receptor field. And besides that, similar to motor cortex, LIP neurons are also active before monkeys secure to its receptor field. And let me take this memory secure task as an example. And in this task, monkeys were required to fixate on the central point, and then a target was displayed transiently in the preview. And after the central point disappeared, the monkey should cut to the position where the target was. And then this red panel showed an example of LP neurons activity when the target appeared in the lab. And we can see the neuron's response was only slightly higher when the target appears and before the movement. But the neuron response changed dramatically when the target appeared in other positions. And here, when the target was in the upper visual field, there were a much larger visual response that begins after the onset of the stimulus and then prolonged activity in the memory period, even without any sensory stimulus. And finally, there is a second peak of activity occurring around the time of the SICAM. And we call this specific region in which stimulus can drive the largest response as receptive. And the neurons can have different, pretty different receptive, basically cover the whole visual field. And Max Sheldon tested the role of LIP in the decision-making task. And this random dots motion discrimination task is a very classic behavior paradigm for studying the perceptual decision-making. And in this random dots task, the monkeys also need to fixate on the central dot, and then two targets are presented. And after that, a random dots motion movie would display. And some dots would move coherently towards one direction, left or right, and the other dots just move randomly. And the monkeys are required to report the net direction of this random dots motion. And if it moves to the left target, the monkey will be rewarded if he cut to the left target afterward. And the right target is rewarded if the dots move towards to the right. And we can control this task difficulty by change the proportion of the dots moving coherently, which we call it coherence or motion genes. And then they recorded the neuron in the LIP when the monkeys performed this task and found a remarkable correlation between the LIP neurons activity and the accumulated evidence. The red panel shows the effect of the motion genes on the LIP neurons fan rate. The average fan rate was sorted by the coherence, which was indicated by the color. And the slope of the fan rate was linearly correlated with the coherence. And when the monkey chooses the target in the receptive field, which are solid line here, the fan rate will reach the same level before the decision. This suggests that the LIP neurons encoded the accumulated evidence supporting the target in the receptive field in this decision-making task. And then Tianming and Mike confirmed this idea, quantitatively confirmed this idea that LIP neurons represent the accumulated evidence during the decision-making process. And in this study, the monkey made a choice between a red target and a green target based on 4 presented shapes in each trial. And the shapes were drawn randomly from this pool of 10 shapes, and each shape was assigned a unique weight. The sum of the weights actually control the probability that a red or green choice will be rewarded, and which actually was the ratio here between the red target will be rewarded and the green target will be rewarded given all presented shapes. And we also call this term log-likelihood ratio. And then they look at the LIP neurons fan rate. The red panel shows the effect of the log-likelihood ratio on the fan rate, just the effect of the accumulated evidence on the fan rate. And the average fan rate was sorted by the log-likelihood ratio in each input. And we can see there is a graded modulation on the fan rate that corresponds to the magnitude of this accumulated evidence. So the population average fan rate could be well described by a linear function of the log-likelihood ratio. But such like accumulated evidence signal has also been found in many other brain areas with almost the same behavior paradigm, such as the dorsolateral prefrontal cortex, the caudate, the superior colliculus. I think it's not surprising because the brain is a highly connected network, but it's really a question of where the evidence signal is computed and central, like other brain areas. And here is our reasoning to approach this question. When the evidence is determined by one single sensory features, then the evidence can be accumulated directly without any other processing. But if the so the sensory feature is actually correlated with the evidence, it will be very difficult for us to discriminate the signal representing sensory cues and that of evidence. But when the evidence is a nonlinear interaction between multiple sensory features, the evaluation of the evidence is non-trivial. It will be much easier to detect the sensory signals, maybe intermediate variables, and evidence at the same time. So we design a probability-based reasoning task in which evidence is determined by stimulus, shape, and color. And if we observe both sensory accumulation and the computation, if we observe both the evidence accumulation and the computation before the evidence accumulation in the LIP, then the interpretation will be that the evidence is more likely to be evaluated locally in the LIP. And the tasks we use are quite similar to that in the Tianling's work, but this task is actually quite complicated. So I'd like to expand all details again. And in this task, the monkey made choices between two targets, also red one and the green one, based on Shakes presented stimuli in each trial. And each stimulus would disappear before the next stimulus was presented. And the stimulus site includes 6 shapes, and each could be either red or green. And the stimuli in each trial were independently and randomly sampling with replacement from this site. And each shape was assigned a weight, the reward probability. But here, the reward probability of the red target is only controlled by the red shapes. And the reward probability of the green target is only determined by the presented green shapes. Consequently, whether a stimulus supports the red target is determined by its shape and color. And then the momentary evidence has to be evaluated based on shape, color, weight, even the target configuration before the evidence accumulation process. So it will allow us to start the sensory evidence transformation process.
I'm sorry, before you move on. So you said the set of shapes are chosen randomly every single session.
Every single trial.
Yes, every single trial. But the value, the assigned weights of those shapes, do they remain constant across days, or do they
across the whole training and the recording process?
Okay, thank you.
So I think another advantage of this task is that the stimulus target association can be defined very freely. And no matter how we assign the weight of the evidence, we can calculate the cumulative evidence at any moment with ease. And this will allow us to establish the correlation between the evidence and the LIP neurons response. Any questions so far? I know this task is very annoying.
Yeah, I get one. So you basically,
yeah,
you repeat 6 times of the shapes. So
different.
in total, you have 12, right?
Yeah, I have 12 stimulus.
Yeah,
12
you have 12. So you randomly choose 6 from them.
Yes. There could be it was sampled with replacement. So there could be the totally same 6 shapes of totally different.
They could be the same or
yeah,
different.
It could be. It's possible.
Okay.
Possible.
Okay. So maybe can you give me an example? For example, let's say the red or the green square means the high probability would be targeted to the right, targeted to the green, right?
Right. So
but if it's a minus value, it means it's a high possibility is the opposite color, right? That is the meaning of the minus value.
Yeah. The next value means that like if there is a green triangle, then that means the reward probability of the green target will be lower than 50%. But it will not change the reward probability of the red target. So the reward probability of 2 targets are totally independent.
Okay.
Yeah.
Just out of curiosity, the 0.54 seems like a very specific number. And
yeah.
Particular reason.
It's like it's the average value if you it's the average value of the 0.3 and 0.9 in the log space.
Okay.
Yeah, thanks for the questions. No more questions? Okay, let's move on. Okay, let's look at the behavior results first. And the left panel is show the psychometric curves. The x-axis is the summed weight of the red shifts minus the summed weight of the green shifts. So when it's possible, that means when it's positive, the reward target, the red target is more likely to lead to a reward than the green target. And the y-axis indicates the probability of choosing the red target. So from this, we can know that the monkey chooses the red target more frequently as the evidence supporting the red target increase. And then we estimate how stimulus exerts on monkey's choice by calculating the subjective weights. And positive subjective weights means that the target with the same color has to be chosen if the corresponding stimulus is presented. And we can find that the monkey assigned positive weight for the shifts with positive predefined weights, and negative subjective weights for the negative shifts. And the rank ordering of this pre-assigned weight and subjective weights are the same. This suggested that a monkey learned the meaning of each shift, although it's not perfect. Then I performed another logistic regression to test whether the monkeys use the stimuli in all epochs. We found that the leverage of the stimulus in all epochs are significantly larger than 0, indicating that the stimuli in all epochs are used for choice. And when the monkeys were well trained, we started to record LIP neurons activity. And we localized LIP area based on the MRI. And when we found a neuron, we will first map its receptor field with this memory cut task. And only the neuron showing a very clear delay response and spatial selectivity in the memory cut task would be recorded and included for further analysis. And during the recording, either the red or the green target could appear in the reset field of the recorded neuron. And we call the target in the reset field. We call the target in the reset field as T-in, and call the other target that was placed in the opposite hemisphere as T-out. And for the neuron data, the first thing I did was testing whether the LP neurons I recorded encode the cumulative evidence as they did in other studies. And the average frame rate was sorted by the cumulative evidence in each epoch, and we can also see a graded modulation on frame rates that correspond to the magnitude of the cumulative evidence. And we further calculated the average frame rate in each epoch and plotted as a function of the accumulated evidence. Here I do that for the T and the T choice separately. And the slope of the fitting lines, we can see the slope of the fitting lines for the T out choice are stable across epochs, while those for the T in trials tend to decrease, which are shown by the red lines. They tend to decrease and become like statistically zero in the last epoch, because the motor signal dominance LIP response in the last epoch, just before the eye movement. And here I just want to show that the neurons I recorded is showing classic LIP neurons properties and is consistent with previous results. And
sorry, can you go back? Can go back?
Sure.
So I quite understand the T in the target in condition. For the target out conditions, the dark 这个蓝色的它是 evidence 更高。这 evidence 更高的意思是它对 out 的 evidence 更高，还是 in 的 evidence 更高？
对 in 的 evidence， 蓝。
对 in 的 evidence 更高。OK， 对 in 的，所以对 in 的 evidence 更高。OK， makes sense. Yeah.
Sorry. Since the weight of the stimulus is the raw materials for this task, for this decision making, so we then sorted the trials by the weight of the stimulus in the current epoch and align it to the stimulus on site. And we found that in both monkeys, the LP neurons responses transiently grow up when the weight was negative, and then would decrease when the weight was positive. And all these lines will merge together about 1 second after the shift onset. And next, we used Poisson GLM evaluated by the Johnson pillow to quantify how the neural responses are affected by the shift weight quantity. And this Poisson GLM specify the probability relationship between the external variable X and the site of neural spectrums. And it's assumed a Poisson noise, and basically they assume the spectrums is the convolution, is the linear convolution between the external variables and the corresponding kernel. And the kernel we get from this GLM could capture the dynamic relationship between the external variables and the neurons spiking probabilities. And then I plotted the kernel the kernel of shift weight for each neuron in the left panel. And each horizontal line here represented the selectivity of the kernel actually of a single neuron. And the color represents the strength of the selectivity. And the neurons are sorted according to the selectivity strength of the weight. And again, here the GLM showed that the most neurons responses are negatively correlated with shift weight after the stimulus onset. And the kernel weight goes to zero gradually, suggesting that the shift weight only had a transient effect on neurons' response.
I'm sorry for interruption. Qualitatively, everything makes sense, but I think we have seen over and over again that between the two animals, there seems to be a slight difference in first in their behavior. The
Yes.
monkey edge doesn't seem to have learned the weights for 3 of the shapes.
Yes.
And also in the last slide in the neuronal data, yeah, this one. We see again that the monkey age doesn't it seems to have a different response in LLP to the representation of the shape and its associated weights. Can you comment on how these differences we see map onto the model? So next slide. Yeah, how do the behavioral differences and the LIP response differences map onto the difference in, the color map that you are showing here?
Okay, I have to admit that the monkey didn't learn the task very well. It seems from this behavior analysis, we can see that although this shape affects monkey's behavior significantly, but its effects are quite smaller than that from the monkey end. So to deal with this problem, we actually use the subjective weight, but not the predefined weight in the GLM. So we actually use what monkey learned from this task to analyze their neuron weight. I think that makes sense, and it won't cause any problem. But you mentioned that there are like two representation. Do means that the first is like a negative correlation, and then it will be a positive correlation. Actually, to be honest, we don't have like too much evidence to show whether monkeys have another peak, but yeah, we don't have much evidence to show you.
Fair enough.
What's the significance of this, the second peak. And we noticed that the behavior difference of two monkeys, so we always show the neuron data for each individual animal for any analysis. Okay. Okay. After we show the kernel of the shift weight, then we plot the kernel of the evidence in the red panel from the same GLM. The neurons in these two panels are sorted in the same order, and we can find that we can see that the most LIP neurons had a positive evidence kernel, which means that the neurons would have a larger response when the evidence was in favor of the target interest activity. And moreover, unlike the kernel for the shift weight, the representation of the evidence was not transient but persistent. And if this weight information was indeed used to calculate the evidence in the LIP, we would expect that the representation of the shift weight would be earlier than that of evidence. And to test it, we estimated the encoding latency of each variable based on the GLM, and we defined the encoding latency as the delay between the shift onset and the beginning of the first significant encoding duration. And then we compared the encoding latency of the weight and the evidence. And here, only the neurons encoding both variables significantly were included. And the results were shown in the red panel. We can, from this panel, we can see that the average latency of the shift weight was shorter than that of evidence, which is consistent with the idea that LIP neurons use the weight information to calculate the accumulated evidence. And another thing I'd like to share about the weight and evidence is that there are separated group of neurons encoding the weight and evidence. Sorry. I think there is a question that whether there are two separate group or there is only one group of neurons encoding this weight and the evidence. First, we showed that in both monkeys, most neurons encoding evidence tend to encode the weight as well. And next, we measured the encoding strings of each variable with CPD. CPD captured the variance that was uniquely explained by a variable. And then the left panel shows the CPD of evidence and the weight and the shift weight. And each dot here denoted a neuron. And we can see there is a clear positive correlation between two CPDs, so that the neurons encoding evidence strongly also tend to encode shift weight. So this evidence suggests that a single pool of LIP neurons encode both weight and evidence. And we know that the shift weight alone is not enough to compute evidence for eye movement decision. And the shift color and the color of key target should also be known. And there are two routes to combine these three pieces of information and compute the evidence. One is first to determine whether the shift color is the same as that T-in's color, which we call it color consistency. And then the evidence is equal to the shift weight if the shift color match the T target's color. And the negative shift, and the evidence will be the negative shift weight if they do not match. And another route is first to combine the shift weight and the color to compute the evidence for the target with the same color, which we call it color evidence, and then determine the evidence based on whether this target is in or out of the receptor field. And we test whether any intermediate terms of these two computation rules were reflected by LIP neurons activity. For neuron M, we found clear color consistency was encoded in the LIP neurons, but not the color evidence. And the response was lower when the color of the stimulus matched the T target's color. And like the shift weight, the shift weight, the color consistency also only had a transient influence on the LIP neurons response. And we also tested the CPD and encoding latency of the color consistency. And the result shows that the CPD of the color consistency was correlated with that of shape and evidence. And also, the average latency of the consistency was between that of shift weight and evidence, which is consistent with its role in the decision-making process. Because you know if you want to calculate the consistency, you need one-step computation. So it will be slower than that of it will be slower than weight. And however, monkey M showed a distinct pattern. The color consistency were not strongly encoded by monkey H. Sorry, here is follow the monkey H. And instead, the color evidence was encoded robustly at the population level, which also in a transient manner. But at individual neuron level, only a few neurons encoded the color evidence significantly. So we don't evaluate the encoding latency and the CPD of this of the color evidence for the monkey H. So summary here, although the LP neurons pattern into monkeys were different, the results from both monkeys showed that besides sensory features and evidence, the intermediate variables in this sensory evidence transformation were also encoded in the LIP. And the last thing is about this accumulated evidence, because you know the accumulated evidence is actually the difference between the evidence supporting T target and supporting T target. So it's correlated with both variables. It's possible that the neurons may be only selective to the log maybe only selective to the accumulated evidence supporting the T target. And actually, it was predicted by another decision-making model called the RIS model. And in the drift diffusion model, as I mentioned, one integrator accumulates the evidence difference between two alternatives. However, in this RIS model, it assumes there are two independent integrators, and each of them accumulates the evidence related to one option. And the decision is made when one of two boundaries is hit. And these two models are actually totally the same when two options are mutually exclusive. And one advantage of our behavior task is that the reward probabilities of two targets can be both very high or very low. In other words, the evidence for two targets are independent in our task, which will allow us to test which model is consistent to what happens in the brain. And here I plot the dynamics of LIP neurons population encoding of evidence supporting T in and supporting T out separately. And we found that the activities of LIP neurons were correlated positively with the evidence supporting T in, and negatively with the evidence supporting T out. So this result suggests that LIP neurons encoded the evidence difference between two choices instead of only the evidence for the T target. And then the panel on the right side indicated the average coding strings for the evidence supporting T in and T out. And the hollow dots here represent the neurons without any significant selectivity. And the blue and the black dots are the neurons which are selective to both variables. And the green and red dots were the neurons that were only selective to T in and T out respectively. And in this individual level, we found that most of LIP neurons also encode the evidence difference between two alternatives, suggesting that a drift diffusion model, but not a RIS model, is in play. Okay, that's basically what we have found. A brief summary here. We designed a probabilistic reasoning task in which momentary evidence had to be evaluated according to multiple features before evidence accumulation. And also, the reward probability of two targets were independent. We found that the sensory features, the intermediate variables required for the evidence evaluation were presented by the LIP neurons transiently, which suggests that the evidence accumulation occurs locally in the LIP. And I think there was only one single pool of neurons responsible for both evaluating the evidence and accumulating the evidence. And moreover, most LIP neurons encode the evidence difference between two choices, supporting this evidence supports the drift diffusion model and not the risk model. And that's it. Thank you, my mentor, Dr. Yang, and my collaborator, Chao Qun, and the lab manager, Kong and Yu, and my monkeys. Thank you.